First speaker for the day is Jayant Murthy from India Institute of Astronautics. I believe that's correct.
Astrophysics.
Yeah. Okay.
Indian Institute of Astrophysics.
Astrophysics. Okay. It was astro something. I do that.
Yeah. Not astrology.
All right. So he's going to present on some of the scientific ballooning sorts of things that that he's been working on in India. And I think this will be a really interesting perspective. And so we'll let him take it away. So thank you much.
Okay, I thought the best thing to do would be to start with the video. It's a 7-minute video, and it was made by one of my students. Who is it playing? Yeah, good. So it was made by one of my students. He later went into wedding photography. So what this was a launch in, I think, 2013. So this was one of our first launches. And I'll tell you how we got into ballooning. I actually come from a space background. I did my PhD at Johns Hopkins, and we did mostly ultraviolet astronomy. Is the video playing for everyone?
Yes.
It's okay. All right, good. So what we were doing is, this is one of our early balloons. And at this time, because it was early in our work, we were using helium. Now we use hydrogen, and I'll get into that a little bit. So this particular balloon was a Chinese balloon. We got a mix of balloons from China, and we got a mix of, and we used balloons from Pavan Rubber in Pune, which I think many people use. We found that the Chinese balloons were quite problematic. They got, many of them had been stitched up. We weren't very happy with them. Pavan Rubber we're pretty happy with. The quality is inconsistent. Sometimes, occasionally the balloon bursts immediately on launch, but they've been pretty okay. So all this balloon had was a tracker, and there it goes off.
Just a quick interject, I did rebroadcast the URL that Jayant's broadcasting, so if this looks terrible on your Zoom screen, you can open up in YouTube, and I just fast forwarded to get to the same place to watch it on another screen here.
Yeah, I'm about 2.5 minutes in. So these are the students who were involved, and it was their first experience, so they're all excited. I found that this is a great thing to get students students interested. And I'll show a picture later when we do outreach at our local university, the Indian Institute of Science, and we easily get 10,000 people coming by and looking at our balloons. We have 2 campuses. This is the Crest campus, which is about 30 kilometers out of the city. So our main campus is right in the middle of the city. This one is about 30 kilometers away. It's about 35 acres. At the time, there was not much around there. Now the area has been built up a lot more, but we still have this big open space. So they launched the balloon, and here they are chasing it. We had a radio transmitter, so with a GPS, and so that's they predicted where it would be from the from the winds, and then they followed it along. In India, sometimes the roads get tricky, so following is not always easy, but there it is. We also have a large number of villages, and no one really knows what the villages are. These kids are all early 20s, 22, 23. So they had fun. They like going on chases. And this is typical terrain for where the balloon comes down. Either trees, scrub like this, or in farmland. So my students, they biked the 30 kilometers from our main campus to there. On the way over, one of the students, he was planning to launch a GoPro, and unfortunately it dropped. He dropped it. A truck, he says, deliberately went over it. He went over the GoPro and then waved at him to tell him where it was. And so this is, so that's pretty much the video. We started, let me close this and start my presentation. Okay, oh great, I can still see the chat window. So as I said, my background is in space astronomy. And what I did for my PhD thesis was a payload on the space shuttle in ultraviolet astronomy. And so about 6 or 7 years ago, we had I had a collaboration with an Israeli group to launch a payload on one of our GSATs, and unfortunately the GSAT exploded. And so I thought, okay, well, I don't want to spend another 5, 6 years, 7 years in a big space mission. So what can I do that a fairly small mission that can be accomplished in not much time? And so this was about the time that the Strand 1 satellite went up into space. This was launched on PSLV. And all they did was they took a Nexus, which they bought in a store, and they launched it on one of these Indian rockets. And it actually worked for some time. And then I thought, you know, if all this time we've been told that space is hard, we have to spend lots of money, spend lots of time, have lots of people, and yet these guys buy a Nexus from the store and launch it. So maybe they're onto something. And that was just about the time that we started what's called an MTech PhD program. So we have a collaboration with one of our universities, and they get an MTech, which is a master's in technology, and then they do a PhD in astronomical instrumentation with us. So unlike most of our students who are straight out astronomy students, these kids their focus is to do instrumentation. And so here are 1, 2, 3, 4, 5, 6 of them. 5 of them were my students. The other guy was an internship guy, a mechanical engineer who just came and worked with us for a year because he thought it was fun. And so what we do is that, unfortunately, and this is the trouble with students, they graduate after a while. You train them up and then they graduate. And so these students, they got good experience in working with balloons. And now they're all working with space missions in different places. Srijat is in Austria. He's working on a mission to look at extrasolar planets. What happens is that the planet goes in front of its star, and they look for the atmosphere of the planet. This is maybe a $5 million mission. Nirmal is in Germany working on another small mission. Ambali is in Colorado. Joyce is in Australia, and Mayuresh is in Singapore. And Ajin is the mechanical engineer who's now working again with us and on other projects. So these students got their start in ballooning, and this is what we primarily use our ballooning program for now. really to get the students a start in working with instrumentation. And when they come in, they're cocky. They build something and they think it'll work right away. And the balloon stuff, it really gives them a kick in the rear end. And they figure out that it doesn't work for one reason or it doesn't work for another reason. And they're all cocky. I mean, they really are. They think they can put something, they come to the site, they put something together, they launch it and think it'll all work. And so this gives them that real life experience. So here, what we do now is we typically launch 3 or 4 balloons. And these are 2 kg balloons from Pavan Rubber in Pune. And again, I think many people use those balloons. We fill them now with with hydrogen. The reason we use hydrogen is because for a while we had a real difficult time getting helium. I mean, helium is an international resource because for medical purposes. And it costs, for us, it costs 20,000 rupees per cylinder, which works out to, I guess, about $300 or $400 per cylinder. And the hydrogen is 700 rupees per cylinder, about $20 per cylinder. So we're trying to do everything cheap, and hydrogen works for us. Because we're doing it outside, I did some research into this, and I think that because we're doing it outside, the hydrogen diffuses out fast enough that it's really not a problem. So, we try not to have any sparks nearby or anything, but really as long as you're outside, the concentration never builds up enough to explode. So the reason we launch 4 balloons is because one balloon, or rather because we're in the middle of this, if you think of the Deccan Plateau of the Indian subcontinent, we're in the middle part of that triangle at the bottom. So we're about 300 kilometers either way from the sea. Typically what our balloons do is that they go about 100 kilometers east, and then they go back to the west. If we leave them for too long, then they cross the mountains and go off into the Arabian Sea. So typically we have about a 3-hour flight time. If we launch one balloon, the rise rate is too slow for us to get very high. We want to go, we pretend to do astronomy. So really we want to go up over 30 kilometers or so, 100,000 feet. And so what we do is we launch 4 balloons. By launching 4 balloons, our ascent rate is something like 5 meters a second or something like that. And so we get up to 30 kilometers in about 45 minutes, 40 minutes or so, if I'm doing the math right. Then we float for about an hour. And then we have a cut down mechanism, which brings our balloons down. It's a timed cut down. We had a location based, but it didn't work too well. So it was a timed cut down mechanism. And it brings it down about 3 hours into the flight. Our students, they start off immediately on launch, and they get to the site probably within half an hour or so after the balloon lands. We've had pretty good success in tracking it with radio. We're not allowed to use satellite phones in India for whatever security reasons. So all of our stuff is by radio and GPS unit on the balloons. We've got our home built unit. Once our cut down mechanism didn't work, the balloons drifted all the way out into the Arabian Sea. I was worried that the Navy would pick it up, so I tried calling our Western Command. No one answered, which, I guess it tells you something about our naval security. And finally, what happened is that some fishermen found it. We have big signs on our balloons telling us that, telling people to telephone us, we'll give them a reward. Usually what happens is that they take whatever they can from the balloons, the batteries, the SIM cards, the camera, and then they call us, and we still have to give them a reward. This time what happened is that the fishermen just took everything, and our guys, they started calling, and the fishermen answered after a while. and we figured out that that they had the balloon. So what happened? Go to the next slide. Yeah, okay. All right, so this is our picture from our obligatory picture from about 35 kilometers. The highest we've been is 37 kilometers. And we measure that in two ways. We have a pressure sensor and we have GPS unit. It takes us it's a little difficult to get the GPS units because you know that the GPS units, either they don't go high enough for their velocity tag because they don't want you using it for missiles. But we get reasonable stuff. Now, the problem with ballooning in India is that we need a lot of permissions. And it used to be that we required permissions once a year. Now we need permissions every 6 months, and it takes them 1 month to give us the permission. So what we have to do is we have to write to the DGCA, our Civil Aviation Ministry, and we also need Ministry of Defense approval. And we still don't have approval to look down because they're worried that we'll fly over some military installation and take pictures. I mean, our cameras don't have the resolution, but anyway, they're worried about that. It's typically not a difficult thing for us, but that is because we are a government center. We're a government research institution, and so it's easier for us. Other people have asked me, and I've told them how to get clearance. It's just not possible. Now, unfortunately, the way that it's really weird. In order to get the information on how to get clearances is classified. So the way we found out is that we went to the military base. The students, we found the number somehow, and our students went to the military base, not too far from my house. They had to get the retinal scan and fingerprints and all, and they went in and they were shown this book which had all the regulations. And at the bottom of the page, it said classified. So they said, you can't take pictures, you can't do anything, but these are the regulations. So anyway, we then wrote to the relevant people and we got regulations. We have to fly medium balloons. In principle, you can fly light balloons without any clearance at all. That's under 1 kg. Under 6 kg, these are medium balloons. And so with medium balloons, you just need clearance. If you want to fly a heavy balloon, which is over 6 kg, then you have to have one of these transponders on board. And when we look for transponders, the transponders are like 2 or 3 kg. So you rapidly increase your complexity. And then we need clearance from all the airports around. Now, when we started, you saw that YouTube video was in the daytime. And so when we started, they were a little more lax about it. And they would let us fly in the afternoon. Now they only let us fly on Sunday night or between Sunday early morning between 2 and 4 in the morning, which is okay. We're astronomers anyway, so we want to look up. So it's okay for us. But that's the only time that there's not traffic in the airport. And we come down pretty close to the airport, so they're a little worried about it. We actually have 4 airports in the neighborhood, and we have to get clearances from all 4 of them. So it takes us about 2 weeks to get clearances. We actually cannot launch in clouds at all because we've done this. We've tried to launch in clouds, and what happens is that our payload box gets completely waterlogged. When it comes down, it's got 2 inches of water in it, and all our electronics goes kaput. So we just can't launch in clouds. And now we've had a real problem this last year and a half. Of course, now with the coronavirus, you guys are in the US are first. I think Brazil is second and we're third. We just can't go anywhere. And so we haven't been able to launch now. But last year was a real bad year for us. The last time we launched was in March of 2019. And normally we have a monsoon season that starts somewhere around, let's say, beginning of July and runs through September. So we're out then. In Bangalore, we get cyclones from both the east and the west coast. That's partly what keeps us cool. We're even though we're 15 degrees south, 15 degrees north, we're at an altitude of 1,000 meters, and whenever it gets real hot in maybe middle March, and then the rains from the cyclones start coming in. So our real launching season is something like December to April, and then again maybe September to November. This last year, because of climate change, we just have had no clear skies. So it's been a year and a half since we launched, just because of this. And we can't wait to get clear skies because it takes us 2 weeks to get clearance. So we try for clearances, and we just can't launch when, I mean, it's just no guarantee that it launches. Okay, I said most of this. So the idea is that when the balloon, or as soon as the balloon takes off, the students take off in a chase car. And you know, the balloon travels at 100 kilometers an hour in a straight line. They go at 60 kilometers an hour along the roads. So typically they're late. This is often the kind of terrain that we land in. And we have, as I said, we have these radio transponders that tell us when we come down. On board the payload, we have GPRS trackers with mobile phones. And typically they tell us where we are within a kilometer or so. The phone coverage has become a lot better over the decade that we've been launching. So now pretty much any area within Karnataka, we know more or less where we are. And they've found the balloon every time. There's been a couple of times balloon landed. They were following the mobile phones, and then they saw that the balloon started moving. It turned out that a farmer had picked it up and was cycling home. So they chased the farmer and recaptured our payload. So anyway, usually we've got it. Sometimes what happens is that the farmers call us, someone finds it, and they call us a week or so later. We had the last payload we launched for, we had a few high school students, and they had an ozone meter on board that they just measured the ozone as it went up. And so we couldn't recover it, but then some farmers picked it up and gave it back. And so these students published a little paper on this. And this is at our outreach at the Indian Institute of Science. They have a public day every year. And anywhere from up to 100,000 students go through, or students, members of the public, students, teachers, parents, they go through the Institute, and we put up a little show. So we have a balloon, we tether it up there, and twice we just let it go. We don't have anything on it, but we just let the payload go. And so students hang around, they ask questions, and so on. So that was our balloon experience. And you know, if anyone wants to know more about what we actually do, about the mechanics of our balloon, I'm happy to take the questions on that either now or at the end. But what I wanted to do was just to tell you a little bit about the other stuff that we do. And as I said, we come in with a scientific, with our reason for doing this is to do science. And so as a result, we insist that all of our stuff is public. It's in the open literature, and we make sure that we publish everything. Because, you know, otherwise we do something and there's no way for us to see whether it's actually worthwhile or not. It should be something that is new, because these students are getting PhDs. And so it should be something that's new and publishable. So the first thing we did was we built an attitude sensor. And the cost of this whole thing is about $50, about 2,000 rupees. It's a Raspberry Pi, And we got an accelerometer and a GPS chip and a magnetometer and put it on. And so it tells us how we're pointed. This is SD card for comparison. We originally thought we would just use a phone, but a phone has so much overhead, that whole structure and all. We thought this would be more efficient. And so this is an attitude sensor. And the whole thing, it's about 200 grams, I think. And you see the size. Well, so we launched it, and indeed, it tells us where our balloon is pointed. Now, because of our balloon program, this is what all the students have a mandate to do. Unfortunately, as I said, we haven't had a launch in a year and a half. So my 2 students now, they have not yet had a balloon launch. But from these balloon launches, they then go on and work on space experiments. And so the first real space experiment that we got was this tie-up with Team Indus. Now, most of you know about the Google X Prize, where they thought they would send a spacecraft to the moon. And the idea was that this would be done by a private company without government aid or without much government aid. And I hope I'm not insulting anyone, but software engineers don't understand science. So what I think these 2 Google guys, they sat down in a restaurant and scribbled some numbers on a paper napkin and said, you can go to the moon for $20 million. Now, it turns out that the launch is about $100 million. So no one actually did it. But we tied up with the Indian company, and what we said is, okay, look, they don't have a launch. They don't have any guaranteed way of getting to the moon, but we'll go ahead and build it anyway. And so this is what we built. And it's basically a telescope that would sit on the lander. And once the lander got to the moon rotates slowly. And so as the moon rotates, we look at different areas of the sky. And so what we would do is we would look for supernovae and other things like that. And this whole thing weighs about 1 kg. We had hoped to have a balloon flight with this. We have a second copy. So we'd like to have it on a balloon flight, but as I said, we just haven't had the opportunity since then. This is a payload. And let me go on to, and this is the actual built payload in our clean room. So this is one advantage that we have that smaller shops don't have, which is that we actually have a class 100 clean room, because we build actual payloads. I have this small thing that really we use for graduate students. The students build things. They build things for the balloon. They build things for space. But we also build. We had an instrument on the space Indian space on the Indian space the first Indian astronomy satellite, AstroSat, and now we're putting something up in L2, so to look at the sun. And so we piggyback on their stuff, and we use the clean room for all this. So Bill says that I was a member of the Google X Prize team, and we determined that it would take 10 to 20 times more than the prize money to land a rover on the moon. Absolutely. And that's why no one did, except for the Bear Sheet guys. They tried, the Israeli team, but they happened to get an Israeli millionaire to give them $70 million or something to go to the moon. It turns out that I mean, just a little side note, that you may have heard about the water bears that they landed on the moon. Now, this turned out to be a real problem, because typically the space guys, they all work on some sort of honor code. So they don't do no one asks them what they do, and in return, they don't do what shouldn't be done. So there's, so these water bears, you're not supposed to go and land stuff on the moon. You're not supposed to put living things on the moon. You're not supposed to take a uranium pile to the moon. And so these guys didn't tell anyone, including the bear sheet guys. They just had their experiment with water bears. And it led to quite a lot of heartbreak, because now they're worried that it'll lead to a lot more regulation, which no one wants. So that was one thing that came out of our balloon program. Now, we want to be, because we're trying to do astronomy from balloons, we need to have a pointing mechanism, and we need to know where we're pointed. And so we developed a star sensor. And so all this is again, we do this on a student budget. So all this is it's basically a CCD with a lens system on front. If you go to the commercial market and you buy something for space, you can spend anything up to $1 million, but the cheapest might be some $10,000-$20,000. So this we built for about $1,000. And what it is it's just a camera. We have a star catalog on board, and so when we look up in the sky, with a cadence of about half a second or so, we can tell where we're pointed. This also is built. We're trying to put it up in space now, but we also are trying to put it up on a balloon mission. Okay. I'll just say one thing here, which is that we have tested it on a star simulator. And the reason we tested it on a star simulator is because our space agency, ISRO, they don't believe the sky. We took it to our observatory and we put it on a telescope and we looked up at the sky and we made sure it worked. But they said, no, you can't do it. You have to look at our star simulator. So I said, the sky is the best star simulator you have. I said, no, you have to do it in our star simulator. So we went and we did it in their star simulator. Okay, and now what we're doing is again, this is stuff that's sort of dual use. We build it for balloons, but then we build it for space. If we have the opportunity, we fly it on a balloon. And so these are, it's a detector that we built in our lab. And one of my students, she got her PhD from this. And the reason we do this is because if you go and buy this from a commercial guy, they'll charge you, it's a fixed price. They look at your budget and then they say, okay, we'll charge you 10% of your budget. And, but really we got the pieces, and we got all the pieces as commercial grade rather than space qualified. And we put it together. And we tried to launch it on a balloon, but we haven't been able to do it as yet. And so this is the final version. This actually we're trying to do in our sister agency at the Tata Institute of Fundamental Research in Mumbai. They have a they have a balloon program. And they have a much more professional program than we do. They stitch their own balloons. We buy latex balloons. They stitch their own balloons out of silk. They've reached 50 kilometers with one of their balloons. With our latex balloons, we can't do much better than 35 or so. And they can carry heavier payloads. So we put together a 15 kg payload with our star sensor, with this detector, and we're hoping to have a flight with that soon. In the meantime, we've also got an opportunity to do this on a space mission. So what universities have worked out is that what universities have worked out is that if they want to use these space missions as advertisements. And so they come to us and they say, we want to have a space mission. So we say, okay, we'll give you the instrument, you build us the satellite. It hasn't worked yet, but we've got some collaborations doing this. And so this is again, the instrument in the clean room. So
hey, Jayant?
the question was, yeah.
We do have a
Yeah, I was
question
gonna-
about
yeah, I was-
how are you stabilizing the astronomy experiments while the balloon is spinning freely?
Yeah, no, so I don't know if I have a picture of that. No, I'm sorry, I don't. What we've done is we've developed a pointing mechanism, and we've tried it in two ways. One was that in order to keep it lightweight, we have a spinning disc in it. And it turns out that you have like a 100-gram disc. If you spin it at 5,000 RPM, that gives you a lot of stability. And we've got a prototype of that we've tested on the ground. We hang it from a hook and we hit it with a stick, and that keeps pretty good stability. We have a more traditional pointing mechanism where we take our star sensor, we take our attitude sensor, we put it on, and we see the problem for the NASA balloons, the 2-ton balloons, they really have good pointing instruments because they have 200 kg pointing payloads. I mean, their pointing infrastructure is 200 kg, but we have to keep it light. And so what we do is we take a fiber and we put it into our telescope. So we have not been able to test it as yet. We had one. The problem is that as you know, balloons are much more stable as you get past I guess the troposphere. I guess you get past about 20 kilometers. But we have not been able to test it up there as yet. So we've tried to test it on the ground, and on the ground everything works fine. We tried to test it on a tethered balloon, but the problem is that on a tethered balloon the winds are way too rough. So we just haven't been able to test it. So we have a pointing mechanism, and I'm happy to share the details with anyone who wants. But we do have a pointing mechanism, we just haven't tested it yet. So what we do now is we do aeronomy. We look at airglow lines, at atmospheric lines, because you don't need pointing for that. We have a fair pointing of the sun. So we've tested it there, and we did have a fair pointing of the sun. But then we started spinning too much and lost it. Okay, so where we are now is that we have one payload on the Chinese space station, and this was through the United Nations Office of Outer Space Affairs, and they had an open call, and we proposed for it, and they accepted it. And what we do is that this is intended to look at things like this. That's a Cygnus loop. It's a supernova remnant. And so what you see is that there's a lot of structure here. And when you have an imager, a camera, all that you get is the structure, but you don't know what the physics of that structure is. So what we have is a spectrograph where you get the atomic emission lines in the different parts. So things like carbon 4, oxygen 3, and by doing that, you get a lot of information about the physical conditions in that payload. I mean, in that area of the sky. And so what we have is it's a little bigger than our balloon payloads. This is about 15 kg. And what we will do is that the Chinese astronauts will take it up to the taikonauts, will take it up to the space station. They'll mount it on the space station. As the space station goes around the world, we observe that area of the sky. And we have another payload where we're trying to get it on an ISRO satellite. Again, we have most of the stuff there. We hope to finish building it within the next 6 months to 1 year. Because of the virus, we've all been affected, and it's going to get quite a bit worse in this area over the next 2-3 months. So the obvious delays, but this is what we're doing. And let's see. I think I'll skip most of this. I'll just tell you that that we've signed an MOU with the Chinese space station with the Chinese Manned Space Authority. We're in a little bit of problem in India now because, as you may have heard, we have some border disputes. So we're trying not to stress the Chinese angle. We're trying to stress the UN angle. But hopefully all these international issues will be worked out and we'll be on the space station in 2022. As far as our balloon program, we are our monsoon is starting now. And so we will hopefully be able to launch our next balloon in early September. And by that time, we should be over much of this virus peak, at least in this area. So let me stop there. I think I have about 5 minutes left for questions.
We'll ask people who have questions, just go ahead and unmute to ask them now. Thank you for using chat.
This the story by Bill here, it reminds us of one of our old Eclipse rockets. They took the rocket up and they wanted to look at the sun in a total solar eclipse. So they programmed it to look at the brightest object in the sky. They forgot that when it was a total solar eclipse, the brightest object in the sky is the Earth. So they got some really nice atmospheric lines instead of solar lines.
Yeah, that was a fun project. We decided to do that about 24 hours before the eclipse because the forecast was for cloudy skies. So we said, let's put a balloon up and watch it above the clouds. And so we had a rudder on the back of it and two photodiodes pointing with a shield in between, so that when they were both illuminated, that was where it tried to close loop. And then the rudder, since the balloon was going up, we're actually flying upwards, would steer it. And it worked great. It was right on the money until the sun went in eclipse and then it started to spin again. But I have a question for you, Jayant. Can you use Iridium modems or Global Star modems like the Find Me Spot for tracking in India?
No, they're all banned. I've tried asking, but they're all banned.
Wow.
But it's basically because they're worried about terrorists.
Huh. Okay. Because I often put one of those on as a backup, and they work great.
Yeah.
You can transmit right from the ground your position.
Yeah.
Well, a great program. I had another question. With the 4 balloons, how do you get your payload to float? Because typically the latex balloon is going to burst when they go up to peak altitude. How do you get them to float? Do you vent them, or do you just adjust the lift so that they don't have enough pressure to burst, or how do you get a latex balloon system to float for several hours?
No, we don't. So we've had a lot of trouble with this because the balloons that we get are, I guess, of reasonable quality, but we very rarely get up to 35 kilometers because 1 or 2 of the balloons burst.
Wow.
And so typically we get up there and then they stay reasonably well at 35 or so. They don't go much higher. They burst at something like 35.
Okay, so they float for a while, or at least you have
float for a while. They float for a while and then we cut them off.
Oh.
So you have 4 or 5 balloons all tied together essentially, and then one of them pops, you kind of go neutrally buoyant, and then you cut down, by time.
That's right.
Okay. All right. That makes sense.
Do you have them separated, or are they all in a line? How do you mount 4 or 5 balloons?
Yeah, so this is a real problem for us. So we tie them together, and especially near the ground, there's a lot of turbulence. So they keep banging against each other. Once they get up, then it's much easier, especially if they get about 20 kilometers. We have a camera looking up, and I can share some of the videos of the camera of looking up at the balloons, so we can see them burst.
I would love to see that. We've flown
Yeah,
3
sure.
balloons, and typically one will burst, and sometimes 2, and then it comes down on one balloon.
Yeah.
We had one land and near a motorcycle off-roading area, and we could see the balloon above the treetops still bobbing around after it landed because we didn't have enough lift to carry the payload back up since we had put 2 balloons on it. And then all of a sudden, the balloon disappeared as we rounded a bend and almost got to the parking lot. And then we saw a pickup truck come out of the parking lot with the payload in the back. We still had to give them a reward. Well, I enjoyed your presentation very much, and I'd love to.
Yes. Yeah.
Please share your email with us. So I'd like to ask
Sure,
for
I'll do that.
in touch with you via email.
And thank you for scheduling me early. It's about what is it now? 8:30 here. So.
Yeah, you're welcome. That was a great talk, and we appreciate you putting us together and joining us. And yeah, one of the downsides for Corona is that we couldn't meet in person, but it gives us an opportunity like this. So thank you very much, and look forward to everyone asking further questions of your setup there. I think there's a lot that can be shared and learned for all of us. So thank you very much, Jayant. And our next speaker.
I have one quick question for Jayant before you go on. Do you have you use APRS on ham radio, right?
Yes.
Do you have an APRS iGate or a digipeater in the region there that is active only during the flights, or do you keep it running throughout?
We keep it running throughout.
Well, that's good, because some of our Pico balloons cross over India, and so that'd be wonderful if you had some APRS. It's 144/800. Is that the frequency you use? I believe.
I can't tell you that, but I can find out.
I think that's the frequency. So I'll email you about the particulars on that.
Sure.
Thanks.